Hi, my name is YilinZhang. Today I will introduce a parallel programming language, which is Go. I believe most of you were familiar with Go, but mostly about concurrency, not about parallel programming. So today's presentation will divide it into 5 parts. Let's start with a fundamental question. Why do we need parallelism, and why should we consider Go for parallel programming? The answer lies in hardware evolution. Modern computers have multiple cores, but writing code that truly utilizes all these cores has traditionally been challenging. Developers have had to deal with complex threading models, blocks, race conditions, and synchronization issues. This is where Go shines. Go's built-in coroutine scheduler enables ordinary developers to take advantage of multi-core systems without having to manually manage threads and locks. The language abstracts away much of the complexity while still giving us the performance benefits of parallel execution. What's the difference between concurrency and parallelism? When I listened to the first lecture, I asked this question. Now, let's clarify this crucial concept that often confuses developers. There's an excellent explanation by Rob Pike, one of Go's creators, that I'd like to share.
But that actually isn't true. Concurrency and parallelism are not the same thing. It's a commonly misunderstood problem, and I'm here to try to explain why and to show you that concurrency is actually better. What would happen to these people who were confused was they'd take a program, they'd run it on more processors, and it would get slower. And they think, this is broken, it doesn't work, I'm going away. But what was really broken was their worldview, and I hope I can fix that. So what is concurrency? Well, concurrency, as I'm using it and as it's intended to be used in the computer science world, is a way to build things. It's a composition of independently executing things, typically functions, but they don't have to be. And we usually express those as these interacting processes. And by process, I don't mean a Linux process. I mean the sort of general concept that embodies threads and coroutines and processes, the whole thing. So think in the most abstract possible sense. So it's the composition of independently executing processes. Parallelism, on the other hand, is the simultaneous execution of multiple things, possibly related, possibly not. And if you think about it in sort of a general hand-wavy way, concurrency is about dealing with a lot of things at once. And parallelism is about doing a lot of things at once. And those are obviously related, but they're actually separate ideas, and there's a little confusing to try to think about them if you don't have the right toolkit. So one is really about structure, concurrency, and one is about execution, parallelism. And I'll show you why those are important. So
let's stop here. Go on, there will be some scenarios that vividly describe it. It's a good video that you can watch it later. Here's the link. Here's the key points that Rob Pike explained. In Go's context, this distinction is important. By default, when you start multiple coroutines in Go, you're working with concurrency. The coroutines may be scheduled to run one after another on a single core. Only when Go max proc is set to greater than 1 can your coroutines actually run in parallel on multiple cores. Then let's talk about the model of parallel programming. Look at this image. You can see here's a GPF scheduler model, which Go usually use. Let me break this down. G stands for coroutine. These are lightweight threads managed by Go's runtime. P stands for processor. This represents logical processes or execution contexts. M stands for machine. These are actual operating system threads. The number of P is determined by either the environment variable GoMaxProx or by calling runtime the function of GoMaxProx in our code. At most, GoMaxProx coroutines can run simultaneously. If GoMaxProx equals to 1, only one core is utilized for execution. If GoMaxProx equals to 4, on a system with 4 or more CPU cores, at most 4 coroutines can run in true parallel. An important historical note: in Go versions prior to 1.5, GoMaxProx default to 1, meaning programs ran on a single core by default. Since Go 1.5, it defaults to the number of available CPU cores, which makes much more sense for modern applications. Looking ahead, Go 1.25 is expected to be released in August 2025, and it will include improvements for handling C group CPU bandwidth limits, which is particularly relevant for containerized applications. Now, let's see this in action with a practical example that demonstrates the progression from sequential to concurrent and then to parallel execution. We'll be working with a prime number finding algorithm to show how easy it is to transform sequential code into parallel code in Go. So, at the left side is sequential version. We only have a simple loop that processes work sequentially. So in the red frame, we could see it divides the work into chunks, but processes each chunk one after another. Each chunk must complete before the next one begins. And for the right side, the concurrent version, we add syn wait group function to coordinate coroutines, and we add the Go keyword to launch coroutines. At last, we need a wait function to synchronization. So even though we are still running on a single core, we use GoMaxProx equals to 1, but the concurrent version can provide benefits through better resource utilization and task scheduling. The Go scheduler can interleave Go routines, potentially improving overall efficiency. Now, let's see the transformation to true parallelism. We only have one key change. It's on line 22. We changed from GoMaxProx 1 to GoMaxProx 4. Now, all 4 Go routines can run on 4 different CPU cores simultaneously. Why 4 cores? Because our algorithm naturally divides the work into 4 chunks. This creates a perfect mapping, 1 coroutine per core, minimizing context switching and maximizing parallel efficiency. Notice that we didn't need to change any of the coroutine code itself. The same concurrent node that worked with 1 core now automatically works with multiple cores. Finally, let's see how we scale to use all available CPU cores. We changed line 14 and line 22. The loop now creates 8 coroutines instead of 4, with smaller work chunks per coroutines. Now we have better resource utilization, with 8 cores available. And we have finer work granularity. More coroutines means smaller work chunks, which can lead to better load balancing. And the function runtime num CPU could automatically detect the number of available CPU cores, making our code portable across different machines. So the progression shows Go's elegant scalability with minimal code changes, essentially just adjusting two numbers. We've gone from sequential execution to using all 8 CPU cores. Then let's see the performance of those 4 versions of code. We can use the command go to traceout to generate those images and tables. It's for the sequential version. Here is the concurrent version. We could only focus on the total execution time of each coroutine in total column. Here, red area represents the execution time of code within a coroutine execution, while the blue area represents the time the scheduler of coroutines had to wait, which is scheduler wait. We can see that a significant portion of the code execution time is taken up by waiting for the scheduler. If we navigate to the view trace page, we can see how coroutines are executed sequentially with interruptions on a single processor. The total program execution time exceeds 480 milliseconds. Here. Now, if we use all 4 available processors, we will see that the execution time is halved. And in the pros area, it is visible that all 4 processors are utilized for performing the calculations. The execution time of each coroutine in the total field has become shorter because the waiting time for the scheduler has been reduced. Thus, by changing the number of processors, we have isolated the execution of our code. Also, if we use 8 cores, we could see the total execution time is even less, but not so obvious. Also, Go has its own parallel benchmark tests. Here's a simple example. We create a simple text template that outputs hello world. It is the work unit that we want to benchmark. Here we have a run parallel function, which is the key to Go's parallel benchmarking. When we call the b.runParallel, it automatically creates Go maxproc number of coroutines and distributes the benchmark work among them. But we should notice that each coroutine gets its own byte buffer. This is crucial. You want to avoid sharing state between coroutines to prevent contention and get accurate parallel performance measurements. We also have the work loop. The for pb.next loop runs the actual work. The benchmark framework ensures that the total number of iterations, which is b.n, is distributed across all the parallel coroutines. The documentation also notes several critical points about using runParallel function. We should use coroutine local state because each coroutine should set up its own local state, like the buffer in our example here. This prevents coroutines from interfering with each other. We also have some global timing functions that we should avoid to use them, like speed.start timer, stop timer, or reset timer, because they have global effects and would interfere with accurate measurement across multiple coroutines. It should also not call b.run. And to be mentioned, run parallel reports nanosecond per operation as wartime for the benchmark as a whole, not the sum of CPU time across all coroutines. This gives us the actual throughput improvement from parallelization. So the benchmark demonstrates that the Go makes it incredibly easy to write parallel benchmarks. Let's compare Go with C++ for parallel programming. Go has some strengths. First, extremely lightweight coroutines. Go can span millions of coroutines with minimum memory overhead. Each coroutine starts with just a few kilobytes of stack space. Second, instant parallel switch. You can dynamically adjust parallelism at runtime using runtime.gomaxprox, making it easy to adapt to different environments. Third, strong built-in tooling. Go includes excellent testing and profiling tools like testing b.run parallel, runtime trace, and pproof right out of the box. Fourth, minimum deployment overhead. Go compiles to a single binary with no external dependencies, making deployment and scaling much simpler. And last, automatic garbage collection. You don't need to manually manage memory, reducing the complexity of parallel programming significantly. But Go also has some weaknesses. GC-induced latency jitters. The garbage collector can introduce unpredictable pauses, which might be problematic for real-time systems, and also slightly lower peak performance for computationally intensive tasks, where optimized C++ code can still outperform Go, especially when you need fine-grained control over memory management and processor features. Therefore, the choice between Go and C++ often comes down to your priorities. Go offers developer productivity and ease of use, while C++ offers maximum performance and control. Here are the references for this presentation. Thank you for listening.